Hello and welcome to this video. I've had a lot of requests from people in person as well as online for me to explain how I design, build, and fly my RC aircraft. This will be mainly focusing on foam board aircraft, though some of the techniques used here will apply to other construction methods as well. My goal here is basically to take you from the inception of the project all the way until the end. I've caught myself right at the very beginning here, and hopefully we should be able to see the plane come together and you'll be able to see the entirety of my design process. Hopefully it'll be useful for you guys. So the first thing I think about when I'm going to build a new airplane is what the airplane needs to do. The reason why this is first is because those requirements will dictate how the design turns out. Take for example the Cormorant 2. This is a craft I originally built in Kerbal Space Program, and I wanted to recreate it in real life using Flight Test's Power Pack F. I wanted it to take off in really short distances, and I wanted it to be able to throw it around the sky pretty good. The resulting plane was really light for its wing area and it had big flaps to allow it to achieve that short takeoff performance. It was also sized so that the Power Pack F motors would give it the thrust-to-weight ratio it needed. Another example is my DHC-4 Caribou replica. I wanted to use twin Flight Test Power Pack C because that's what I had lying around, and I wanted it to be able to do the wheelbarrow, which is basically get enough deck angle with enough flap deflection such that the nose is actually pointed down when the plane is flying level, so that you can plant the nose gear on the ground and keep the mains off the ground. This is a maneuver that the real Caribou did, and I wanted to replicate it in RC. Now, if your plane is a replica, like those two were, the design requirements regarding the physical size and dimension of the aircraft are pretty constrained because what you're replicating has a specific geometry. But if you have a clean sheet design, you have a lot more freedom to choose what the aircraft will end up being. An example of this was my Efflux Mk. It was a testbed for a variable area outlet nozzle for a ducted fan. The main requirement which constrained the design was that I wanted to get the fan and the nozzle both out into the airflow as one, so that I wasn't dealing with any confounding data of any inlet ducting or anything. I wanted to have a flight controller on board and a pitot tube so I could measure the thrust versus the airspeed as I played with the nozzle setting and constricted it and opened it up. Another example is the Efflux Mk, which was my next sort of iteration in clean sheet research-based designs. For this one, I was experimenting with trailing edge circulation control. My goal for this project was to redirect the EDF exhaust out at the trailing edge of the wing and blow it over flaps so that I could actually change the flow field around the wing and get extra lift coefficient out of it artificially. And so this drove a lot of the design with regards to placing the EDF near the wing so that I could get the ducting to work out properly, as well as the consideration of using the existing electronics from the Efflux Mk to save money. So that brings us to the aircraft that I'm going to try and design here. The inspiration from this came from the Rockwell X-31, which was a thrust vectoring high alpha research testbed. And so I want to do something similar. I want to do thrust vectoring and high alpha, and I also want to use the electronics and other hardware in the Efflux Mk to save cost. Now that we have these requirements down, we can start to think of the possible solutions in terms of aircraft configuration that would meet these requirements. Typically, you'll want to explore these potential solutions by sketching them out and just seeing if you can think about what works. You can do this with pen and paper, or you can use an image editing software. I'm going to use paint.net. So when high alpha is involved, the thing I immediately think about is just delta wing, because I've had good experience with delta wings in the past, especially at high angles of attack. Delta wings, especially the lower aspect ratio ones, are pretty inefficient, which means you can get them to fairly large angles of attack before they start to stall. So that's sort of better if you're looking at getting just purely angle of attack without any aerodynamic consideration to it. But also that'll make the transition into post-stall flight a bit easier because it's sort of easier to get up on the thrust of the aircraft with the nose pointed more towards the sky than it would be otherwise. Here's another design consideration. The gear I have isn't going to be retractable, it's going to be fixed. And what that means is that if we want to minimize drag and get this plane going decently fast in the top end, which I would like, in addition to going slow, we're going to have to do our best to minimize the drag from that fixed gear. And if I think about ways of doing that, one of the best ways is probably to overlap the cross-section of the gear with the cross-section of existing stuff. So we might as well do that with the wing, because if we try and do it with the fuselage, it'll probably be too close together and it'll tip and probably hit a wingtip or something. So the top of the main gear is going to protrude into the wing, and then the main gear is probably going to be reasonably far out on the wing, at least farther out than the fuselage. If we think about it side-on though, the wing is probably going to look something like this from the side, some sort of approximation of an airfoil. So the main gear is probably going to end up somewhere around there. And if we're overlapping the main gear with the wing, the fuselage isn't going to be able to come below the wing much. So this is going to end up being a low wing aircraft. So our fuselage is probably going to end up looking something like this, just very generally. I did say the gear were going to be wider than the fuselage, so we'll make that consistent. And so now we can figure, we'll put in our thrust vectoring stuff here. So this will be our nozzle. And that'll probably stick out past the end of the fuselage, or past the end of the wing. And then here's something to consider. If we're doing high alpha, we're going to want to be able to do high alpha landings. So that means that whatever sort of angle here, if you imagine this is the ground, we're going to want that angle there to be pretty steep so that we can come in and land at relatively high angles of attack. So that means that this main gear is probably going to be more towards the aft of the wing here. And so what that means is it's probably going to be pretty far behind the CG. And so if we were going to try and put some sort of tailplane back here to push down on this to lift the nose up, it's probably not going to work too well. So the best solution I can see in this consideration is to put a canard on it, because instead of pushing the back down, now we're lifting the front up. And it's a lot easier to do that around this when the CG is, say, like right here. And so I'm going to put a canard on it, probably somewhere around here-ish. Maybe give it some sweep so it looks cool. And then of course it needs a vertical stabilizer. I think we'll just keep it simple and make just a single one. That's all I have the servos for anyways. So something about like that. It's probably too big, just eyeballing it for now. Again, this is just conceptual design. This is just to figure out like the relative placement of everything and the configuration of the aircraft. None of this has any real geometric significance in the long run. Now, since this is a conventional landing gear configuration, we're going to have to put the nose wheel somewhere, so it's probably going to go up here. And then that sort of limits our intake, because we can't have an intake on the bottom here like the X-31 did. And I don't really want to put the intake on the top because then it'll get bad airflow at high angles of attack. So it'll probably end up on the side of the fuselage. Let's draw a front view here. And then our inlets are going to be on the side. So they're going to come out like this. And then probably, they might be square, they might not, but now here's something. If this is going to be here, the canard's there, do we bring these inlets forward and then put the canard on them? I'm liking that idea because the canard airflow won't disturb the inlet airflow if we do that, whereas if we did something like this and we put the canard in front of the inlet, then the canard's inlet would disturb the airflow into the inlet. And we could like high mount the canards or something, but I also like having the canards sort of close to the plane of the wing if we could, just for their vortex generation capability at high angles of attack. So I think what we'll end up doing is putting the canards pretty close to the top plane of the intake there. And in fact, it might actually be better in the final design to make these inlets a bit wider like that, so that we can get the canard pretty close to the plane of the main wing. So now we can start thinking about control surfaces. For the delta wing, I think I'm just going to go with elevons. There'll be something about like that. They'll probably be fairly large to deal with the high alpha we'll be doing. And then I think I'm also going to put some slats on them, just again to help with higher angles of attack. So maybe something about like that or something. And then the canards will probably just be used for pitch control. I think I'll only have enough servos to do entirely pitch control if I do the slats or the leading edge droop. Obviously the proportions of this are quite off, but the idea is there at least. In fact, I think I'll probably just move this back so that it'll be closer to what it actually be. Get that canard closer to the actual wing. These canards, I think they're going to be all moving, just so they have maximum effectiveness. And that's something I want to try out. So here's something else I'm thinking about. Ideally, you want the airflow at the fan of the ducted fan to be very similar to that of free stream conditions. And so the only really good way to do that, especially if we're going to be doing high alpha and a lot of low airspeed stuff, is to make these inlets really, really huge, like probably twice the fan swept area. But of course I don't want to do that because that means extra drag up on the top end. So what I'm thinking about doing is, because especially we're going to be needing a lot of static thrust at high angles of attack, is actually putting in some sort of door on the bottom of the fuselage that will allow air, let's say our fan is going to be right here, this is going to be our fan face, that will allow air to come up from the bottom of the fuselage and into the fan. It'll essentially be like a toggleable cheater inlet, basically. And this will probably all be flat down here. And so that'll be on the bottom of the fuselage here. And so then our ducted fan is going to be about here, our fan face, and then we'll have a thrust tube inside the aircraft that'll go all the way to whatever nozzle we have at the back. That'll do the thrust vectoring stuff. And in front of this, we're going to have some sort of inlet ducting to go into the fan. And then for the CG to work out, the battery is probably going to have to be just probably around here, somewhere around there at least. That'll put it right about there. Maybe it goes on top of this inlet section if it needs to be back over the inlet. So the battery will end up probably around there. And that should get the CG pretty close to where it needs to be. So that's it for this episode. Just a quick and dirty conceptual design of what I think I'll end up building. Next thing we're going to do is we're going to go into some performance calculations and get our initial sizing of everything done. And until then, I'll see you.